This is the presentations produced by Stephen. I will be working through a question based on the MO diagram, and there was 20 marks in total. From what we can see from the first part of the question, it asks us to draw the MO diagram for N2. Also need to write down electron configurations and explain how this agrees to triple bond expected from the Lewis structure. So as we can notice from the periodic table, nitrogen has the atomic number of 7, which gives it 7 electrons by itself. So the electron configurations would be 1s2, 2s2, and 2p3. There will be 5 electrons in its valence shell. It would be 2 in 2s orbital and 3 in 2p orbital, which each would be representing px, py, and pz. So here is the template of the MO diagram for N2 I draw on the left hand side. There will be 3 different energy levels, which is 1s, 2s, and 2p. On the side would be the atomic orbitals for nitrogen, and this part would be the same. The next step is to fill in the electrons. We know there will be 2 electrons in the 1s orbital and 2 in the 2s orbital, and there will be 3 in the 2p orbital. I will be using a different color to represent the 2pz, the reason I will talk about later. When 2 nitrogen combines together, there will be bond formed in between. For 1s and 2s, it will simply just be sigma bound and anti-bound orbital. For the 2p, it will be different because of the presence of the 2pz electrons. There will be the formation of the pi bound just in between the sigma bound, and up here will be the anti-bound pi bound and anti-bound sigma bound. The next step is to fill in the electrons. For 1s and 2s, it will be quite simple, just fill in as you go. As for the 2p orbital, it will be quite different because the 2pz electrons will actually fill in the sigma bound, while the 2px and 2py will fill in the pi bond here. If we count up the electrons in between the bonds, we would get a number 14, which is exactly what we expected before we draw this diagram. To calculate the bond order of N2, we simply just take away the anti-bonding electrons from the bonding electrons and divide by 2. In this case, it would be 4 anti-bonding electrons and 10 bonding electrons, which we may get an answer of 3. What can we discuss about this number? To begin with, it is a diamagnetic species. And second, there is a triple bond presented in N2 molecules. If we draw the Lewis structure of the N2 molecules, it would look something like this. There will be a triple bond presented here and 2 electrons in the outer shell. So for triple bond, we know a triple bond is made up of 2 pi bound and 1 sigma bound. So let's link back to the MO diagram we draw for N2. There happens to be 1 sigma bound and 2 pi bound presented in the 2p orbitals, which is what we expected from the bound order and the Lewis structure we draw. And this will be the end of part 1, question 3. For the second part of the question is to do with the MO diagram for CO. So carbon has the atomic number of 6 and oxygen has the atomic number of 8, which gives their electron configurations of 1s2, 2s2, and 2p2. In the oxygen it will be 1s2, 2s2, and 2p4, 2 more electrons. As for the electronegativity, oxygen has a slightly higher one, so in carbon, the electronegativity is 2.55. and for oxygen is 3.44 instead. Here is the MO diagram for CO. So we've got 4 electrons in the outer shell of carbon and 6 electrons in the outer shell of oxygen. That makes the total number of 10 outer electrons to be accommodated in the molecular orbitals of CO molecule. Because of the higher electronegativity of oxygen, its atomic orbitals would be of lower energy than the corresponding atomic orbitals of carbon, which in this case would look like this on the left. On the left hand side would be the atomic orbitals for carbon, and right hand side will be the atomic orbitals for oxygen. So for carbon, there is 2 electrons in the 2s orbital and 2 more in 2p. Apologies, this should be 2p orbitals. And for oxygen, it will be 2 in 2s and 4 in 2p, which is slightly different. So while we are filling the electrons, we may calculate the bound order as well. So we've got 2 electrons in the anti-bonding orbital, and we've got 8 in the bonding orbitals, which makes the bound order of 3. The bound order of a CO and N2 be the same. So we've got triple bonds presented in both of the molecules, and we've got 1 sigma bound and 2 pi bound here, and 1 sigma bound and 2 pi bound here. Due to the energy difference, the bounding and anti-bounding molecular orbitals will actually receive different contributions from the atomic orbitals of carbon and oxygen. The bounding molecular orbitals will receive more contributions from the atomic orbitals of the lower energy, like the atomic orbitals of oxygen, and would be closer to it in energy than the anti-bonding molecular orbitals, which would be closer to carbon in energy. Before we start doing part 3 of the question, I will start by drawing an MO diagram for O2. So this will be the atomic orbital for O, this will be the atomic orbitals for O. And we know the electron configurations of oxygen is 1s2, 2s2, and 2p4 by previous questions. So we've got 6 electrons to be accommodated in the MO diagram. And as we can see, oxygen molecules have 2 unpaired electrons in the lower pi anti-bonding states. And for O2 2+, we simply just remove the 2 unpaired electrons in the anti-bonding pi orbitals, as they are the most easily to be removed. So the MO diagram for O2 2+ will look like this. So the sp mixing occurs when the s and p orbitals have similar energies. The energy difference between the 2s and 2p orbitals in oxygen is greater than that in nitrogen. Because of this, oxygen by itself are not sufficient to change the energy ordering, and their MO diagram will follow the normal pattern. But if there's a charge presented like O2 2+, it will be the same as all the other period 2 diatomic molecules where they do have sp mixing, which leads to the pattern like what we've drawn on this slide here. We can also add in the electrons and determine the molecular electron configurations and bond order for each of the diatomic molecules. When we do so, if the bond order of a molecule we predicted is equal to 0, then those molecules are not existed. So for the last part of the question is we need to calculate the bound order of O2 and bound order of O2 2+. For O2, we've got 4 anti-bonding electrons presented and 8 bonding electrons presented here, which the final result is equals to 2. So there's a double bond presented in O2 molecules. For O2 2+, the removal of 2 electrons in the anti-bonding pi orbitals, which look like this. So we've got, instead of 4, we've got 2 electrons for the anti-bonding orbitals and the bonding electrons are still 8, and the final result is 6/2, which equals to 3. So there is a triple bond presented for O2+. The removing electrons from O2 removes the electrons from the anti-bonding orbitals. The order of a covalent bond is a guide to its strength, and the bond between two given atoms becomes stronger as the bond order increases. So if there's electron presented in the anti-bonding pi orbitals, it would be a double bond, and if not, it would be a triple bond instead. This will be the end of my presentation. Thank you for watching.